Our objective in this video is to construct a utility function. Now recall that our goal in constructing a utility function is to get a function which represents how we value the probability distributions on the reward space. In other words, we want a function so that we can take the expected value of that function using these different probability distributions on the reward space, and the numeric values will be ordered in the same way that our preference among all of the probability distributions on the reward space. So I will encourage you to read pages 48 and 49 in the textbook. They go through in detail about how to construct a utility function. We're going to do this in a sense. We're going to look at example 4. And so this example is about what to do on Saturday. And so there's two options. We can either go see a football game or we can go to the movies. And we really would like to go see this football game, but the problem is there's a chance it may rain. So we have two choices. So we can take two actions. Action A1 is that we go to the football game, and A2 is we go to the movies. And then, of course, the unknown here is whether it rains. So theta 1 will be it rains, and theta 2 will be no rain. And so there's 4 possibilities and 4 consequences, or 4 rewards. And I would encourage you to write down what each one is. Okay, so R1 is the situation where it rains, we go to the football game and it rains. R2 is the situation where we go to the football game and it does not rain. I think if you look at that list of preferences, I think you will agree that R1 is the worst. If we go to the football game and we get rained out, that's going to be like the worst situation. If we go to the football game and it does not rain, then that's the best situation. So then the question is, what about these other two? So R3 is where we go to the movie and it rains. R4 is where we go to the movie and it does not rain. And so you may be wondering, why do they have R4 listed as worse than R3? And the reasoning in the book, and this makes sense, is that if it does not rain, but you chose to go to the movies, then you may be upset that you could have went to the football game. Whereas if you go to the movie and it rains, then you can be happy that you made a wise decision. Okay, so that is how the book ordered the preferences, and I would tend to agree with that. But we need a little more. We need to assign a utility to each one of these rewards, each one of these consequences. The way the book is going to instruct us to do that is going to be to assign a utility of 0 to the worst reward and a utility of 1 to the best reward. And then from there, we'll have to decide how to assign utilities to these middle two. So the mechanism we're going to use to assign utilities to those rewards R3 and R4 will be with what the book calls a gamble. So let's say, so essentially our objective then is to pick the right alpha here. So let me try to explain. Suppose alpha were 0.5. Basically what that means is you've got a 50% chance of the reward being R1 and a 50% chance of the reward being R2. So in other words, you've got a 50% chance of the worst case scenario occurring and a 50% chance of the best case scenario occurring. Well, that's even worse off than the actual state of nature, right? The actual probabilities reported by the weather service or whatever. Because the weather service said there's a 40% chance that it's going to rain and a 60% chance that it's not going to rain. Suppose now let's say that alpha is 0.2. What if you could go to the football game and it doesn't rain with an 80% chance, as opposed to going to the football game and have it rain with a 20% chance. That would be the case where alpha is 0.2. So the question we have to ask ourselves is, what alpha would we require so that we would value that distribution on the reward space exactly the same as for sure reward R4, which is the situation where we go to the movies and it does not rain. And that's a decision you have to make. Which alpha would you choose, and you would value either one to be the same? In other words, you would say, I don't care, either one is valued the same to me. So here in my notes, I posed the question, what about alpha equal 0.99? Well, if alpha is 0.99, that would mean there's a 99% chance that you go to the football game and it rains, as opposed to a 1% chance that you go to the football game and it doesn't rain. That would be terrible. And I think any reasonable person would say that there is more utility in the reward where you go to the movie and it does not rain for sure. How about if alpha is 0.01? So that means you have only a 1% chance that you go to the football game and it rains, whereas you have a 99% chance that you go to the football game and it does not rain. That would be very good, especially considering that in this problem, you really want to go to the football game. So in that case, there would be more utility over here. That's a chance, you're almost sure that you're going to have the best reward occur. Now, it's not 100% sure, but you're close. So those are two extreme options. What we've got to do is nail down which alpha, right? Like I said before, what we need to do is nail down which alpha would we pick, and we would consider both of those as the same. We would choose either one just as quickly as we'd choose the other. And of course, which alpha you pick is your own preference. That is a function of, that depends on the specific decision maker. For the sake of argument, let's say that our choice of alpha is 0.4 here. And so we're going to value the reward R4 for sure just as much as we would value this probability distribution in which we experience the worst reward with probability 0.4 and the best reward with probability 0.6. So we're going to assume that we value both of those exactly the same utility for both of them. And you can see the snippet there from the book. So in other words, you would just as soon see the movie and have no rain occur as you would play this gamble of having a ruined afternoon with probability 0.4 or the best afternoon with probability 0.6. And so then once we make that decision, once we make this decision up here, then we can calculate the utility associated with reward 4, because it's the same as the utility associated with this on the right, which is 0.4 times the utility at R1 plus 0.6 times the utility at R2, which gives 0.6. Okay, the last one is to figure out how much utility to assign to R3, and remember that's the situation where you go to the movies and it rains. And remember that's a situation that was deemed a little better than R4 because in that situation you would have made the right decision. So let's see if we can find a beta so that we value the reward R3 with certainty the same as if we had a gamble between worst reward R1 and the best reward R2. So then let's say, for example, we choose beta equals 0.25. Then the utility for R3 is 0.25 times u of R1 plus 0.75 times u of R2, which turns out to be 0.75. And now, since this is a subjective process we're going through, you may want to do consistency checks until you get a set of utilities that you're comfortable with, no matter which way you look at it. Okay, so with that said, here is the utility matrix, and utility is just going to be the negative of loss. So we're not really changing so much what we're doing from the previous chapter. It's just that instead of looking at things in terms of loss, now we're looking at things in terms of utility. So in this case, bigger numbers are better. So you can see with R1, if we decided to go to the football game and it rains, then that's the worst situation. And so that had a utility of 0. The best situation was the situation where we choose to go to the football game and it does not rain, and then that's where we assigned a utility of 1. And then we assigned utilities for the other two, as you see there. Also, recall that we were given a prior distribution on theta, so we know from the weather forecast that there was a 40% chance of rain. So then, now let's decide what to do. If we choose action A1, then we're looking at the first column in the utility matrix. So, our utility, our expected utility, would be the utility of R1 times the probability that it rains, plus the utility of R2 times the probability that it does not rain. And as you see there, that turns out to be 0.6. Now let's look at the second column and see what the associated value is for action A2. So if we choose action A2, then we have the utility of R3 times the probability that it rains, plus the utility of R4 times the probability that it does not rain. And you see there that the expected utility is 0.66. So given this utility function, then the correct decision for this particular decision maker would be action A2, because for that person, their expected utility is higher than with action A1. So the optimal action is to go to the movies.